Okay, what's up, everybody? Hey, today we're gonna wrap up curves or titration curves. I'm gonna explain a few things about it. So I just want to highlight a couple things in the AP exam as you continue your review over stuff. So we're doing those progress checks. So again, I don't care what you score on them. Try the best. They're meant to be diagnostic. The idea is that you can figure out what area you might need to study on. So, for example, um, Unit one, Unit one is like electron configurations, trends, structure stuff. That's 7 to 9%. So both of these. So this is the one we just did with like electron configuration. We didn't really just do that, but this is the one we just did, bonding, that kind of stuff. But the one that's really, really big is Unit three. So this one is super important because this one's like all the intermolecular forces. You can see this like 18 to 22%. So understanding the types of bonds and how it affects all the properties, whether it's a gas, a liquid, or solid, that's super important. So this one I want to highlight. Everybody should spend some time reviewing Unit three. Reactions, this one is like chapter 4, like net ionic reactions. Kinetics, we did pretty well on as a class, but it's 7 to 9%. So that's something that you can, that's only one chapter, and one chapter reviewing that's super huge. Um, Thermodynamics, again, 7 to 9%. So that's like delta S, delta H, that kind of things. And then equilibrium. So I want to mention these ones. This is like what K is, Ka, but acid base, this is where the buffers fall. So it's not a huge portion, but it's pretty big. And buffers are just part of it. So honestly, it's probably about 5% of the test will be like buffers and titration curves, but it'll definitely be on there, 5 to 6%. And then this is like electrochem at the end. So electrochem, that's on there. So you'll see all those. So go through all of them should be opened up, all those AP classroom stuff, and you should be reviewing, right? Like you get one go at this and it matters. So go for it, man. Get your score and you can be done with chemistry forever. Or, it's really hard. You can become an AP Scholar of Distinction, which is super awesome, especially in AP Chem. This is hard stuff, man. And you guys have done it and you totally can. You don't need me. All right. You're good enough. Okay. So I want to do a quick review of buffers. So buffers are an interesting thing. So at their basic thing, buffers, these resist change to pH. And what that means is that they have something in them that fights off an acid or fights off a base. And what you have to have is and this is the only way, it has to be a weak acid with its conjugate base. Okay, so something like HF, which is a weak acid, and F minus. And usually this F minus comes in the form of like NaF because Na is always a spectator, right? Or you can have a weak base and its conjugate acid. So this is a really good one too. You could have NH3, which is a weak base, remember, ammonia, and NH4 plus is its conjugate acid. So every weak acid has a conjugate base, all that kind of stuff. So to know this, let me get rid of that for a second. The easiest way to do all of these, and normally I'd be like, hey, and you can solve these with ice problems. But if it's a buffer problem, and you're going to know it's a buffer because it's going to be like two things. It's going to be like, all right, what is, I'm just going to do a real short one. So HC2O4 minus and then C2O4 minus 2, right? So this is a weak acid. This is its conjugate base. That's how you recognize it right away, as you're going to see like it's two component. Okay, so when you see these, jump right into and do this. Jump right into the pH equals the pKa plus the log of the base over the acid. And usually what happens is normally you have to do concentration, and it just depends on what they do, but because they'll typically have the same volume, these can just be in straight moles too. So this one actually works in moles on both of those. Now, I want to mention about capacity and like what makes a good buffer. So a rule of thumb is, and if you look down here, this is like a pKa list. So Ka, this is like usually given to you, and you just take the negative log to find the pKa. Pretty much is these exponents with where they're at. So if I'm going to make a buffer with a pH of 4, okay, so I want it to be 4, like what chemicals should I use? Okay, and to do this, what you have to know is you have to know the pKa's of these. So can I do it with this? Oh, heck no. So what has to happen is this typically the pKa needs to be plus or minus 1 of the pH I'm looking for. So if I want a pH of 4, I can use this one. I could actually use all of these right about here because they're all plus or minus within a 4. And what that means is these values will be pretty much close to each other. The acid and the base will be, that's what you want. You want something, you want a lot of acid and a lot of base in your buffer because then what it can take on, it can resist change to pH. So if I want a pH of 7 and I have to make a buffer, okay, so if I want a pH of 7, I have to make a buffer. I'm totally using this guy right here. I can even do it with bases. So if I want a pH of 10, I can use these guys right here. Anything within plus or minus 1 of the pKa is a good buffer. And you just have to kind of adjust the amounts to make it happen. Okay? So buffers are tricky. There's lots of math with them, but they don't have to be hard. Just use the Henderson-Hasselhoff equation, Hasselbalch equation. I always call it Hasselhoff. Okay. Now, today what we're going to do, and what we're going to try to do is we're going to look at acid-base reactions. And there's another way you can make buffers, and that's through titrating them. So when you take an acid plus a base, you get a salt plus water, right? So I'm going to get here. So I'm going to go boom, 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 right? This is just simple reactions. This would be something they would ask. So I get water and K2SO4. Whoa, that's a 4. Okay. Then what I would do is I'd balance it because I don't want to be breaking the law. And I think this is it, right? Okay, so then what you should know is that when you add an acid to a base, they neutralize each other. That's a key concept in chemistry. And we've done a ton of titrations. And unfortunately, we won't be able to do the titration curve one, but it's okay. We don't need to. I think you can get the gist from a graph, from like a couple pictures and some notes. Okay, so a titrant, this is our known substance. This always goes up here. So typically it's been NaOH. It can be anything. So, and then this is your analyte. This is over here, this guy right here is your Erlenmeyer flask, your burette. Oftentimes in the AP test, they're going to ask you a question like, all right, tell me about the lab. And you're going to have to like pick out equipment, read how many sig figs, all stuff that we've done. Okay. No one has to be a superhero. Remember our numbers: 80% for a 5, 65% for a 4, and 45% for a 3. And I'll grade that like that too. So, but you've got this. We got this totally. Okay. All right. So, anyways, titration curve. We're going to tell you guys an alternate way of doing this. So, normally, what happens is you add, base, and then it changes color. This time, you don't have to add any indicator to this one. All you do. Okay. So, this is just. I kind of want to mention this before I go too far. So, understanding like how much acid is needed to neutralize stuff is important. So let me give you this one just so we have it. So 20 milliliters of 0.3 m NaOH is required to neutralize 30 milliliters. What's the molarity? So when you're doing acid-base titrations, we're trying to find the endpoint. And so it's always molarity times liters equals moles. And for this one, you check your equation, but this is going to be 1-to-1. So you can actually use this formula: molarity times molarity of acid, volume of acid is equal to molarity of base times volume of base. And the reason why you can do it is right here, right? So like these guys will equal the moles of the other one. So just to show you, I'm going to do 20 times, what is it, 0.3, that's these guys right here, is equal to MA times 30. So basically I'll do 20 times 0.3 divided by 30, right? And 2/3 of 0.3, I think, is 0.2, which makes sense. So the molarity of the acid is 0.2. That's just solving for it there. And these are done the same way. This is just like with a strong, it's just like, so this is a strong acid, strong base. It's just straightforward. And the endpoint of these, since we kind of talked about this before, but like hydrolysis, like the endpoint is going to be 7 if you take a strong versus a strong. Okay, so I'm not going to do these. You've got that. Okay, now sometimes you're going to have to read these cool things called like titration curves. And what I want to mention with this curve is that this is how much base you had. So usually it's in milliliters. And then you're going to measure the pH. And what we know is if we take a strong base with a strong acid, the salt, because of no hydrolysis, it'll have a pH of 7. And so what happens is as you add base, so picture this, you're dripping base, drip, 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 and it's going in. Because this part you have excess acid, the pH is super low. And then over here, once you've passed, and some of you have done this too, you've passed the endpoint, you have excess base, the pH is above 7. But if you hit that point where it's exactly equal acid to base, it'll have a pH of 7. And so what you just have to know is you just have to know the areas. All right. So at the beginning, I have excess acid because I haven't reached endpoint. At the end, I have excess base because I've gone past it. Think like dark pink, right? And then understanding that this amount right here for 7, once you've reached equal moles, so the point when one drop turns it equal, it's going to have a pH of 7. So a strong is going to have this shape. It's going to have it's going to have a really low pH at the bottom, high at the top, and the inner point, like the in-between point, is always the equivalence point. That's when moles are equal. So moles of A equals moles of B. Okay? So reading a titration curve for strong, it can be crazy and scary, but it's not. All right? It's just straightforward. So strong is straightforward. So here's what you typically have to know. So you typically have to know this point, which is the initial pH. And to find the initial pH, you just negative log it because it's strong. So for example, if I have initial acid of 0.1 m HCl, if you negative log 0.1, which is how you find it, the pH would be 1. So the pH is 1, the pH is 0, whatever. And then the equivalence point is here, and that's always 7. So you just have to know this point, and you have to describe that there's excess acid and there's excess base. Remember, if you go past the endpoint, you have too much base, the pH is above 7. If you haven't gone to the endpoint, you have too much acid, it hasn't gone. So for these guys, that's why I say you just need conceptual. Okay, so before, after, during. All right. Now, weak acids, it's a whole different story. So these ones have some unique features that are going on, and I think it's important to know. First off, this is what it's going to look like. Instead of it having, the real steep, low, high, and then 7, what it's going to have is it's going to start off higher. Okay, so it starts higher. And the reason why it starts higher is it's a weak acid. So weak acids have higher pHs. They don't fully dissociate. It's also going to have this slow area where there's buffering. And I'm going to talk about why it buffers in a second. But this area right down here is a buffering region. So like you'll add it and the pH doesn't change much because buffers by definition don't change pH. And then the end point is going to be above 7 because when you take a weak acid with a strong base, okay, first of all, it's always going to be of 7, but it actually, the salt you make actually hydrolyzes water because this guy right here is the conjugate base of a weak acid there. And so it actually reacts with water and forms a base. So what happens is you have a really fun type of problem here, and I'll explain it. So at the bottom, because it's going to have this one, so this point right here, the initial on our graph, so it's going to look like this. So pH, and then this is milliliters of base added. Okay, so you're going to have to know this initial spot. And this initial spot right here is an ice problem. And an ice problem for a weak acid is when you take the Ka times the initial concentration and do all that kind of stuff. And then this whole spot right here is the buffering region. So buffering. And then right here is the endpoint, and this is a hydrolysis problem, and it's above 7. Okay, now I know this is confusing, so that's why I'm gonna hit it up in the next slide too. Okay, so here it is again. So the 3 points that you have to know right here, and then I'm going to talk about this point, which is halfway to the end point. So again, ice problem. This is actually the pH equals the pKa, and that's because the amount of base present is equal to the amount of well, so HA in this sense, which is your acid, is actually equal to A minus, um, at least in concentration. Here, all of the acid has been converted and all the base has been neutralized. But right here, these values are equal. So it's called the half equals equivalence point. And I'll show you that too. This is fun. I've never taught this online. This would be okay. So let me give you this one and then we'll work through this and see how it goes. Okay. So calculate the pH of the solution formed when various volumes of 0.1 are added. Okay. So first off, let's write the net ionic. So we have NaOH plus HC2H3O2 arrow, and then it would be NaC2H3O2 plus H2O. And if I were to, and that's how it always is, like it's always a salt with water, right? So if I take the net ionic, I'm going to get rid of this, and then this has to stay together, the acetic acid. So it's going to be OH minus plus, because NaOH is a strong electrolyte. Things that dissociate are salts, bases, that kind of stuff. Weak acids do not. Arrow, and then C2H3O2 minus plus H2O. That's my net ionic. Okay. So then my initial pH of my solution before it drops added. So what we're on in our graph, again, our graph, we're down here. Like what's the pH before you add a drop of base? So what you have to do is I'm going to give you guys a shortcut. So the pH is equal to the negative log of the Ka times the initial concentration, square root of. So this is the way you would solve it. It's the shortcut. So I can work my way through the ice problem if you like, but basically what happens is the acetic acid, I'm just going to say HA, reacts with water to form H3O plus and A minus, right? So when I do this, Ka is equal to H3O plus and A minus all over HA, where HA is acetic acid. I'm just shortening up for you guys. And then you would solve for H3O plus. And so basically the solution for this is the pH is equal to the negative log of Ka times initial. Remember, we always get rid of X. We've done a lot of those problems. So anyways, you would do that. So I'll show you guys what that would look like. So pH equals the negative log of the square root of 0.1 times 1.8 times 10 to the negative fifth. And that'll give you your pH. So for weak acids and weak bases, you can always use this shortcut. Maybe list out your ice problem and all that. Okay, now second, I want to mention this. So if I add halfway to the endpoint. So what I mean by that is, see how 50 milliliters would neutralize it. So if I take 0.1, if I have 50 milliliters of base and 50 milliliters of acid, like they're totally neutralized because they would cancel out. They would be equal amounts of moles. But here I have 25. And what will happen is I'm going to show you guys the reaction. So I'm going to put HA, because again, it's shorter, but this would be acetic acid plus OH minus. And you see how I would make A minus, which is my conjugate base, plus H2O. So here, if I have, let's just do this. So if I have 0.5, okay, that's how many, actually it would be 0.1 times, let's do this. So 0.1 times 0.05. So that's molarity times volume in liters would give me 0.005 moles. So if I have 0.005 moles and I add 0.0025 moles, do you see how this would react? And I'd be left with 0.025. So now, and then I would make 0.0025 of this. So in this case, so my conjugate base and my acid, they're equal. So when you add half as much acid, what happens is HA is equal to A minus. This is super important. So the reason why this is important, if I plug this into my pH equals pKa plus the log of base over acid, when these guys right here, base, are equal to each other, you would have the log of 1, which is just 0. So at this point, the pH equals the pKa. That is always the case on our curve, is that the pH always equals the pKa right here. Okay, so we're on our little thing right here. This is my equivalence point, and this is my halfway point. So I'm halfway to this. This is always the pKa. So what you do to find this spot is you take the negative log of this, so negative log of Ka, and you would get 4.74. I just memorized it. Okay, it's one you commonly use. And then finally, once you've neutralized all of the acids, so now all the HA is gone. Okay, so A being acetic acid. Okay, and now all you have is A minus. What you have to do is you have to find the pH of a bunch of A minus. And the way you do that is this is how you would do this one. Okay, let's do this one. These are hard. So we're going to spend a couple days on this, and I'll probably come in for this at some point and do a couple. I hate to spend all this time on like 5%, but it might make the difference for someone. So we're going to do it. We're going to go for this. Okay, so this is the hardest part, finding the pH. So it's a hydrolysis problem. So we're going to find A minus. Okay, so A minus plus H2O yields HA plus B plus OH minus. And this is going to be above 7 when we find it. So if you get a pH of like 4, be like, oh, I did it wrong. Okay, so to do this, what you're going to do is you have to find moles. So the way we find moles, and we're going to find molarity, okay, is remember how we said that we have 0.005 moles of NaOH. And so what's going to happen is, and I'm going to write my equation out here again, just so you can see it. So we have HA, acetic acid, plus OH minus yields A minus plus H2O. Okay. So these are equal. And if I add 0.005 moles of this, these are both going to react. So it's going to be 0.005 and minus 0.005. And I'm going to make 0.005 of my salt. Okay. Now, before we do an ice problem, though, this is in moles, and this guy needs to be, because we're going to do an ice problem here, this needs to be in concentration. So I have 0.0005 moles made, again, right here when I react them. And then to find concentration, you have to divide it by volume. So what I'm doing, though, is think about it. I had to add 50 milliliters of acid and 50 milliliters of base. So this is actually divided by 0.1. And the reason is 50 plus 50 gives me, this concentration right here is always moles divided by total volume, and the total volume at endpoint. And usually they don't try to make it super hard, but sometimes they do. So then this would just be what, 0.005 divided by 0.1, whatever that is. I can't think this morning. Okay. And then this is going to be minus X, and this is going to be so that would be basically times 10 then. So it'd be 0.05 minus X. And then this would be 0 and 0, and this would be plus X and plus X. And so anyways, your X squared would be 0.05 is equal to, okay, now it's not equal to this Ka. And the reason why is that this guy, A minus, is actually a base. So what you have to do is you have to take Kw divided by Ka to give yourself Kb. So again, this would be Kw divided by 1.8 times 10 to the negative fifth. So then you have to do a bunch of algebra. You got to solve for everything, solve for X. And after you solve for X, then what you have to do is you have to take whatever this is. And I'm going to not do this. I'll let you do this part. And you'll practice this, and we'll try this. But what you have to do then is you have to take the negative log. And what's really crazy is it's going to be, it's the POH because it's a base at this point. So you have to subtract from 14. So now, needless to say, I'll give you a video to work through some extra calculations on these. These are tricky, but we can do it. Okay. Now, this is just the opposite of it. So it's the same thing, but it's just done a little bit opposite. Again, I'm just going to highlight the spots. This is an ice problem. This would be the pKb because this is a base. So this is a weak base. And then the equivalence point would be less than 7. Again, if you take a strong acid plus a weak base, you get a salt that is less than 7. This is hydrolysis. Okay. This would be, and you don't, they took this off the AP test, but this is a diprotic acid. So what happens here is this is the first H coming off, and then this would be the second H. This would be pKa1, pKa2, and this would, this is the same kind of thing. Actually, this guy right here, since it's strong, has a pH of 7. So the first H coming off is a pH of 7. So you don't have to do an ice problem for that one. Okay. And then, all right, so if we summarize this, just really understand this part. They're going to give you some sort of pH curve, so you just kind of have to know how to use it. But a weak acid with a strong base, the pH is greater than 7. At this point, right, for my weak, it's a hydrolysis problem. This would be my pKa, and then this would be an ice problem. So that's what you have to know. Strong, these are the easiest because if you take a strong acid with a strong base, it get pH of 7. And then weak acid plus, or weak base plus strong acid lower than 7. So in this question, it's just a quick review question. Two acids are titrated versus strong base. Which one represents the strong acid? So totally two, right? Strong acids have a low pH, so they start over at the bottom. This guy right here, since it's a weak acid with a strong base, would be my buffering region. And are the two acids the same concentration or different? They're the same because it takes the equal amount of NaOH to cancel both of them out. And that's how you know. Okay. Now, when you do a titration, sometimes I'll refer back to like, all right, what's a good indicator for it? And so you have to kind of know the type of titration and how it fits with the types of indicators. So if I have a weak acid with a strong base, my pH is going to be be equivalent lower than 7. So if I use phenolphthalein, I'm going to miss that part. And if I miss that part, it doesn't work. So I need something that hits the range of that. And what they'll often do is give you like the pKa of it, which is the color it changes at that. So neither of these would work. For this titration, which is a strong acid with a weak base. Okay. And all right, let me go next one. Maybe it. That might be it. Okay, yeah. So when you see this, you'll see questions of these. You just have to pick one that fits. All right, that was a lot. I'm sorry. This is hard. I know you guys are doing a nice job. We're almost done. Just hang in there. Yeah. Okay. So we'll talk to you later. See you guys. Take care. Hopefully you're going well. Let's pause this thing. Stop sharing. Stop it. Just